Imagine that you are sitting in front of a computer at 2 in the morning, and suddenly a news item appears on your screen, a single line. No beating around the bush, no context, no preparation. Cambridge scientists find strongest evidence of life beyond Earth. You read it again, slower. It's not science fiction. It's not a movie. It's not speculation from an obscure internet blog. It is the University of Cambridge. They are real astronomers, real data. A space telescope that cost $10 billion and that spent years being pointed at a specific point in the sky. And that point has a name, K218b. In April 2025, those 5 letters and a number became the most searched on the planet. And for a very simple reason. For the first time in human history, scientists weren't just saying that maybe there was life somewhere else. They were saying they had found something. A sign, a molecule, a chemical fingerprint that, here on Earth, only exists because something alive produced it. And that changes everything. Or it can change. Because the story of K218b, and it's this story that we're going to tell you now, is not simple. It is exactly the kind of story that science produces when it is operating at the limit of what human instruments can perceive. A story of discovery, of doubt, of intellectual dispute between brilliant minds, and of a question that has never left the heart of humanity. Are we alone? This question is not new. Socrates did it. Giordano Bruno was burned for suggesting that he did not. Enrico Fermi at lunch on an ordinary day in 1950 looked at his colleagues at the table and asked, "But then, where is everyone?" And humanity has never been able to stop thinking about it. What has changed now is that, for the first time, we have an instrument capable of responding, not with assumptions, not with philosophy, with data, with specters. By reading the chemical composition of an atmosphere 124 light-years away. And the data said something that no one was completely prepared to hear. The telescope that changed the game. To understand what happened to K218b, you need to understand what the James Webb Space Telescope is and why it's unlike anything that came before. The James Webb is not only bigger than Hubble, although it is. It's not just more potent, although it is that too. What Webb does fundamentally differently is that it sees at wavelengths that the human eye has never been able to reach. He sees in the infrared. He sees the heat. It sees through clouds of dust that block the entire visible spectrum. And, most importantly for this story, it can read the chemical composition of the atmospheres of planets orbiting stars tens, hundreds, even thousands of light-years away. How? Through a technique called transmission spectroscopy. When a planet passes in front of its star, what astronomers call a transit, a small fraction of the star's light passes through that planet's atmosphere before reaching us. And every molecule in the atmosphere absorbs light at specific frequencies. It's like a chemical fingerprint. Methane absorbs at certain frequencies. Carbon dioxide absorbs in others. Water vapor has its own signature. And the dimethyl sulfide DMs, the molecule that is at the center of this whole story, has its own. James Webb was launched in December 2021, after decades of development and delays, when it finally unfolded into space. 5 million kilometers from Earth, and its golden mirrors aligned. It was a moment that many scientists described as the most exciting of their careers, because that instrument was the first tool in human history really capable of searching for life beyond the solar system. And one of the first targets astronomers chose was K218b. It was not by chance. K218b was originally discovered in 2015 by the Kepler Space Telescope. At the time, it was just another number in a growing catalogue of exoplanet planets orbiting stars that aren't our Sun. But some of its characteristics soon drew attention. First, your location. K218b orbits a red dwarf star called K218 in the constellation Leo. This star is 124 light-years from Earth, a distance that, in cosmic terms, is neighborhood. In human terms, it is inconceivable. The light coming out of K218b today will arrive here in 124 years. Any message we sent would not be answered for at least 248 years. Second, its position in relation to the star. K218b orbits within what astronomers call the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. Not too hot, not too cold. The Goldilocks zone. Third, its size and mass. K218b is a world entirely different from anything else in our solar system, with a radius 2.6 times that of Earth and a mass 6 times greater. It falls into a category called subneptune, planets larger than Earth but smaller than Neptune. Here in our solar system, we don't have anything like that. But out there, they're the most common type of planet we know of. And then came the hypothesis that changed everything, that K218b could be a Hycean world. The term was coined by Cambridge University astronomer Niku Madhusudan, the same scientist who would later be at the center of the DM's controversy. Hycean is a combination of hydrogen and ocean. In English, Hycean from hydrogen and ocean. The idea is that these planets would be covered by global oceans of liquid water, surrounded by hydrogen-rich atmospheres. If this is true about K218b, imagine what it would be like in this world. A planetary ocean, with no continents, no land in sight in any direction, under a sky of a different color from our own, illuminated by a cold red star. And in that ocean maybe, just maybe, something alive. To find out if this hypothesis was substantiated, scientists needed to look more closely, and Webb did just that. The first clues, 2023, and the weak signal in September 2023. Madhusudan's team published the first James Webb results on K218b, and those results were already enough to make the world of astronomy vibrate. The telescope had detected, with unmistakable clarity, two carbon-carrying molecules in the planet's atmosphere, methane and carbon dioxide. It was the first time in history that molecules of this type had been detected in the atmosphere of an exoplanet, located in the habitable zone of its star. That, in itself, was extraordinary. But there was something more. Amid the data, there was a weak signal, tenuous, uncertain, a spectral pattern that, when scientists compared it to known molecules, seemed to match the dimethyl sulfide DMs, the same molecule that, on Earth, is produced almost exclusively by marine life, mainly by phytoplankton, the microscopic algae that inhabit the planet's oceans. The staff was careful. They did not announce that they had found life. They said that there was a possible detection, that it needed validation, that more observations would be needed. But the implication was there, written between the lines of every paragraph of the scientific paper. If that signal was real, and if it was really DMs, and if DMs came from where it always comes from on Earth, then K218b could have life. The scientific community reacted with enthusiasm and healthy skepticism in equal parts. It was exactly the kind of result that needed independent confirmation, and the Cambridge team got back to work. April 2025. The announcement that shook the world on April 16, 2025. Niku Madhusudan and his colleagues at Cambridge published a new paper in the prestigious astrophysical journal Letters. This time, using the James Webb Mid-Infrared Instrument, a different camera, sensitive to wavelengths that the first observation had not covered. What they found was more than they expected. The DM signals were stronger, much stronger, and there were also hints of another related molecule, dimethyl disulfide DMDs, a compound that, on Earth, is also associated with biological processes. Together, the two compounds appeared at concentrations that the team estimated to be 10 parts per million, thousands of times more intense than the concentrations we found in Earth's atmosphere. The statistical confidence level achieved by the team was 3 sigma, which, in probability language, means that there was only a 0.3% chance that the data was random noise rather than an actual signal. In everyday terms, this compares to the probability of flipping a coin 10 times and drawing heads every time. Madhusudan chose his words carefully, but the impact was immediate. He described the findings as the strongest evidence yet of life on another planet. Not confirmation, not the proof, the strongest evidence. The world has not made this distinction. In a matter of hours, newspaper headlines around the globe announced, in bold letters, "Scientists find life on distant planet." Social networks exploded. Television presenters broke the normal schedule. Politicians spoke out. Religious leaders were questioned. The question that humanity has carried with it since it learned to look at the sky finally seemed to have an answer. But science doesn't work like that. The voice of reason. What Avi Loeb said in the midst of the frenzy. One voice stood out for its sobriety. Avi Loeb is a Harvard astrophysicist, one of the most daring and controversial researchers of his generation. It is the same scientist who, in 2023, led an expedition to the ocean to recover fragments of an interstellar meteorite, and who believes that the metallic spheres found at the bottom of the ocean may have an extraterrestrial origin. a hypothesis that he continues to investigate with his characteristic defiant enthusiasm. Loeb isn't afraid to ask questions that others avoid. But when it comes to extraordinary claims, he also knows that extraordinary claims require extraordinary evidence. And that's exactly what he said about the K218b. This molecule is produced in the Earth's atmosphere by microorganisms in the oceans, he explained. And there are those who claim that perhaps this planet has oceans of water. Although this is also disputed, he acknowledged the interest of the discovery. But he immediately put the caveat that many headlines had ignored. The question remains whether this could be produced by something else. And to be completely sure, physicists need a confidence level of 5 sigma, which is closer to 99.99%. 5 sigma. This is the standard that physics uses to declare a definitive discovery. It's the difference between it looks like something's there and we can bet our reputation on it. In particle physics, it was the standard used to confirm the existence of the Higgs boson in 2012. In the field of exoplanets, biosignature had never been achieved for a chemical signature of life. 3 sigma is equivalent to flipping a coin and drawing heads 10 times in a row. 5 sigma is equivalent to doing this 20 times in a row. The difference is huge, and Loeb, with his characteristic mixture of curiosity and rigor, pointed out this abyss with surgical precision. It also brought to light another element that the headlines had overlooked. DMs had already been detected in comets, on chunks of rock and ice that wander through space without any sign of life, which meant that the molecule, by itself, was not proof of biology. It was just a clue. And clues, as any good investigator knows, need to be followed very carefully. Science answers the debate that followed. What happened in the months following the April 2025 announcement was something rare and valuable. Science working exactly as it should. Independent teams around the world pored over the James Webb data. They used different methods, different models, different statistical approaches, and what they found was disturbing for those who expected a quick confirmation. Louis Wellbanks, a researcher at Arizona State University, led one of the most detailed studies. His team noticed a fundamental problem in Madhusudan's original analysis. The models used to identify the molecules were too restricted. When expanded to include a wider range of compounds, the DM's signals simply disappeared. Other hydrocarbon compounds that have nothing to do with life produced spectral patterns, indistinguishable from DMs in the available data. When the model was expanded, the evidence for dimethyl sulfide just disappeared, Wellbanks said. A conclusion that any honest scientist will recognize as the kind of result that demands attention. A second team, led by Raphael Luke of the University of Chicago, combined all of Webb's available observations of K218b in near-infrared and mid-infrared and came to a similar conclusion: insufficient evidence for DMs or DMD. Instead, they found signs of ethane, a simple hydrocarbon that doesn't suggest biology. A third study, by Kevin Stevenson and colleagues, was even more straightforward. The mid-infrared data was so susceptible to instrumental noise that reliable conclusions simply couldn't be drawn from it. Depending on how the data was processed, anything could appear or disappear. In August 2025, NASA led its own reanalysis with Ren Yuhu of the Jet Propulsion Laboratory and the participation of Madhusudan himself. The result was a nuanced portrait. The planet's water was confirmed to be abundant. Possibly half of the mass of K218b may be water. Methane and carbon dioxide have been confirmed. The DMs, however, appeared only at the 2.7 sigma level, below the 3 sigma of the original paper, and far below the 5 sigma needed for a conclusive statement. The strongest evidence for life beyond Earth had become, in a matter of months, tantalizing but insufficient evidence. What it teaches us about science. This is where the story of K218b stops being just about astronomy and starts to be about something bigger, about how humans build knowledge in uncharted territories. It's tempting to see what happened to the K218b as a failure. Scientists have announced something, other scientists have questioned it, and now we're back to square one. Right, wrong. What happened was the exact opposite of a failure. It was science doing what science does best, testing its own conclusions, resisting pressure to confirm what we want to be true, and preferring honest uncertainty to false certainty. Think about what was at stake. Confirming life on another planet would be, without exaggeration, the greatest event in human intellectual history. It would change our philosophy, our theology, our biology, our understanding of the place we occupy in the cosmos. A statement of this size cannot be supported by data that, depending on the method of analysis, simply disappears. And the scientific community, with all the imperfection and competitiveness that characterizes it, has recognized this. It was not necessary for any authority to decree that the announcement was premature. Other researchers simply looked at the data, tried to reproduce the results, failed, and published what they found. This is the scientific process. Imperfect, sometimes time-consuming, often frustrating for those who expect quick answers, but infinitely more reliable than any alternative. Madhusudan himself, rather than retract or abandon the research, said that subsequent studies were encouraging and that they were enabling a healthy discussion about the interpretation of the data. He remains convinced that more data, more hours of observation from Webb, may eventually clarify whether DMS is there or not. He estimated that just an additional 16 to 24 hours of James Webb's time on K2-18b could be enough to bring the data closer to the 5 sigma threshold. The telescope has decades of useful life ahead of it. More observations will come. February 2026, the search continues, and strange, in February 2026, the story of K2-18b gained a new chapter, this time not with photometers or spectrographs, but with radio telescopes. A team of researchers used two of the world's most powerful radio telescopes, the VLA in the United States and Meerkat in South Africa, to listen for K2-18b, not to look for molecules in the atmosphere, but to listen to radio signals. The kind of signal that a technological civilization could be transmitting, analogous to our own telecommunications technology. The result? Silence. No narrowband radio signal was detected coming from the K2-18 system. If there's a civilization there, it's not transmitting anything that our instruments can detect, at least not with the power of a transmitter equivalent to the old Arecibo radio telescope in Puerto Rico. But what may seem like a disappointment is actually science advancing. The study set upper limits on what could exist there, and it has developed automated signal filtering systems that can be used in future searches. In science, knowing that something is not there is just as valuable as finding what is. In addition, the absence of radio signals says nothing about the presence of microbial life. Bacteria, algae, phytoplankton, the kinds of organisms that could produce DMS in alien oceans, do not transmit radio signals. The search for intelligent life and the search for simple life are completely different questions, answered by completely different tools. And K2-18b remains, in Madhusudan's own words, after NASA's analysis, our best chance to study a potentially habitable environment beyond the solar system today. The planet in detail. What we know for sure. In the midst of all the controversy over DMS, it's easy to forget what James Webb clearly confirmed about K2-18b, and what has been confirmed is extraordinary in itself. The planet has water, lots of water, probably more water than anything in our solar system, except perhaps the icy moons of Jupiter and Saturn. Some estimates suggest that water may make up to half of the planet's mass. There is methane in the atmosphere. It has carbon dioxide. It doesn't have ammonia in significant amounts, which is important because ammonia should be present in abundance if the planet were a mini Neptune of gas. The absence of ammonia is consistent with the idea that the planet has a liquid ocean that absorbs this gas. The planet orbits in the habitable zone of its star, receiving an amount of solar irradiance similar to that of Earth, its equilibrium temperature, ignoring the greenhouse effect of its hydrogen atmosphere, is between -23 and -27 degrees Celsius. In the presence of the greenhouse effect, it can be warmer, it can be too hot, it may not be. All of this means that K2-18b is genuinely intriguing as a candidate for a living world. It is not an icy planet frozen billions of kilometers from its star. It's not a superheated rock hell. It's a world with liquid water, with carbon in its atmosphere, at the right temperature, in the right place. And it's the kind of world that, just 10 years ago, we didn't have any tools to learn anything other than size and mass. The DMS issue, still open, so, is DMS there or not? The honest answer, in March 2026, is, we don't know. The signal exists in the original data. Independent teams have confirmed that the signal may be there, but may also be explained by other molecules, by instrumental noise, or by geological and chemical processes that do not involve life. What we do know is this: The original detection was statistically weak for a claim of the size that was made. This does not mean that the Cambridge scientists made a mistake in publishing. Publishing preliminary results with clear caveats is part of how science works. The problem occurred when the media and the public turned tentative evidence into proof of life. We also know that DMs, even if confirmed, would not automatically be evidence of life. The molecule has been detected in completely lifeless environment. In 2024, a study showed traces of DMs in a solar system comet, confirming that abiotic processes unrelated to life can, under certain conditions, produce the molecule. This does not eliminate the interest of the signal in K218b, but it does complicate the interpretation. And we know that, for the level of confidence necessary for a historical statement, data is still lacking. Madhusudan estimates that a few dozen hours of additional Webb observation may be enough to clarify the issue. New instruments, such as the future extremely large telescope under construction in Chile, may eventually resolve the ambiguity even more precisely. The search continues. The question remains open. And that, interestingly, is some of the best news possible, because it means there's still a lot to discover. The distance ladder, how we got here. To fully appreciate what is happening with K218b, we need to take a step back and look at the path that has brought us to this point. 30 years ago, we didn't know if there was a single planet around any star other than the Sun. The idea that other solar systems existed was reasonable but not confirmed. In 1995, Michel Mayor and Didier Queloz detected the first exoplanet around a Sun-like star 51 Pegasi b, a gas giant 50 light-years away. They won the Nobel Prize in Physics in 2019 for this. Since then, the acceleration has been dizzying. The Kepler telescope, launched in 2009, alone has discovered more than 2,600 confirmed exoplanets today. We know of more than 5,700 exoplanets, with thousands of candidates awaiting confirmation. And the K218b was one of many, until Webb started looking at it closely. What Webb has done is move exoplanet exploration from a science of detection to a science of characterization. Before, we knew that planets existed. Now, we begin to know what they are made of. What gases inhabit their atmospheres? What temperatures can prevail on their surfaces? What chemical possibilities are there? It's the astronomical equivalent of going from seeing a light on in a distant window and knowing that someone might be at home to starting to hear the sounds coming from inside the house. We haven't been able to get in yet. We still can't see faces. But what we hear is enough to know that the question is worth asking. What humanity has risked asking. There's something profoundly human about what's happening with K218b, which goes beyond science. When the Cambridge astronomers published their paper in April 2025, they knew the data was uncertain. Madhusudan himself was careful in his public statements, repeating that further observations were needed, that it was not a definitive statement. And yet, the world reacted as if humanity's oldest answer had finally arrived. Why? Because the question, are we alone? It is not a scientific question. She is philosophical. It is existential. It is the question that lies beneath all the others we ask about our origin, our purpose, and our destiny. She is as old as the first person who looked up at the starry sky and wondered what lay beyond. Different human traditions answered this question in different ways. Some religions claim that we are unique, created in a special way in a universe created for us. Some philosophies argue that the uniqueness of human consciousness is itself evidence of something extraordinary, and science that cannot address meaning, only facts, goes where the data takes it. And the data, for now, point to a planet 124 light-years away, with water, with carbon, at the right temperature, with a faint signal that may or may not be the trail of something alive. Avi Loeb, with his characteristic frankness, captured well the dilemma facing scientists. If there were life on the planet, it might be difficult for us to communicate with it. Any signal sent to the planet would not be answered for at least 248 years. That's a long time. I don't have the patience to wait 248 years. And then, with the lightness of someone who knows exactly how things work, he added, it would make a lot more sense to listen to them. On a good date, when you go out with someone, the best advice I can give is, first listen, then talk. The 5 sigma pattern and the story IT tells, the number 5 sigma, appears several times in this story, and it's worth stopping to understand what it really means, because it reveals something important about how science deals with extraordinary claims. In statistics, sigma is a measure of dispersion, a way of quantifying how unlikely it is that an outcome is the result of chance. 5 sigma means that there is only a 1 in 3.5 million chance that the observed result is random noise rather than a real phenomenon. This pattern is not arbitrary. It exists because the history of science is full of discoveries that later turned out to be statistical illusions. The phosphorus signal on Venus, announced in 2020 as a possible indication of life in the planet's atmosphere, disappeared when the data was reanalyzed more carefully. Exotic particles that seemed to break through the standard model of particle physics appeared and disappeared. In medicine, a significant proportion of the results published in prestigious journals cannot be reproduced by other laboratories. The 5 sigma standard exists to protect science from its own animosity in heralding the new and the extraordinary. And in the case of K218b, he's doing just that by asking scientists to accumulate more evidence before making a claim that can't be undone. This does not mean that the presence of life on K218b is unlikely. It means that we don't know yet. And we don't know yet is an honest and valuable answer. The universe of possibilities. Beyond K218b, the K218b is not alone. While the controversy over this specific planet unfolded, the James Webb continued its work on other targets. And what began to emerge was a portrait of the cosmos that was far more habitable than many expected. Rocky planets in habitable zones. Atmospheres with water on worlds that once seemed unlikely candidates for life. Complex organic molecules in clouds of interstellar gas, the building blocks of the chemistry of life, scattered throughout the universe as ingredients in a cosmic stockpile. The biology we know on Earth is based on carbon, hydrogen, oxygen, nitrogen, phosphorus and sulfur, common, abundant elements distributed throughout the universe. The chemistry that produces amino acids, precursor molecules of life, has been observed in meteorites, in comets, in star-forming regions. Life, at least as we know it, seems to be no improbable accident requiring unique conditions. It seems to be the predictable result of chemistry under certain conditions, and these conditions seem to exist in many places. Astronomer Frank Drake, who formulated the famous equation that bears his name in the 1960s, an attempt to estimate the number of technological civilizations in the galaxy, never expected to live to see exoplanets being studied with such granularity. The Drake equation was always more of an exercise in thinking than calculating, because the values of almost all of its terms were unknown. Today, 2 of the most important terms, the rate of star formation and the fraction of stars with planets, are known with good precision. And what we do know is that there are more than 100 billion stars in the Milky Way, and that most of them probably have planets. If only a tiny fraction of those stars have habitable planets, and if only a fraction of those planets have developed life, we would still be talking about an astronomically large number of inhabited worlds. The question is not whether life exists somewhere beyond Earth. The question is when, and how, we will prove it. The lesson of Venus, when science gets class wrong. This isn't the first time a possible biosignature on another planet has sparked excitement and subsequent review. In September 2020, a British team announced the detection of phosphine, a gas that, on Earth, is mainly produced by bacteria in Venus' atmosphere. The headlines were similar to those of K218b. Scientists find possible sign of life on Venus. In a matter of months, other researchers found serious problems in the analysis. Most astronomers today believe that the original signal was an artifact of how the ALMA radio telescope data was processed. Phosphine on Venus, as evidence of life, did not survive scrutiny. The Venus episode is instructive, not because science has failed, but because it has worked. One group made an interesting claim. Others tested it. The results were not sustained. The community has revised its position. This is the natural cycle. And now the same cycle is underway with K218b. The difference is that in the case of K218b, the data are richer, the planet is more promising, and the instrument that is making the observations, the James Webb, is of a quality that Venus has never had. The validation process is more complex, because the planet is more interesting, and the claims are deeper, but the process is the same, and the result, whether confirmation or refutation, will arrive in the same way, through accumulated data, rigorously analyzed by multiple independent teams. The comment of the comments, what the public understood. It's worth watching how the public reacted to the K218b announcement, because the reaction reveals something about our collective relationship with these issues. On social media and in the comments of videos on the topic, a pattern repeated itself with remarkable consistency. Unlike other major science news, where the public is often divided between believers and skeptics, the K218b news generated a predominantly philosophical reaction. The most liked responses did not celebrate the discovery or dismiss it. They reflected on the nature of human knowledge. "How can you misunderstand something we never understand?" asked one comment with thousands of likes. "The universe is not broken, our map is just incomplete," said another. "The path to wisdom begins with, I don't know." This is revealing. The public, even those with no scientific training, intuited something that the headlines often hide, that science is not a collection of certainties, but a process of progressive reduction of ignorance, that each discovery is not an endpoint, but a new starting point. And the story of K218b is a perfect example of this. A tempting result, a scientific community that tests it, an unexpected twist, and a horizon of new questions richer than the previous ones. This is not a failure, it is living science. What's next? The horizon of observations, the story of the K218b, is far from over. In fact, in many ways, it is still in its infancy. James Webb will continue to observe the planet. More mid-infrared data will be collected, processed by multiple teams, compared, debated. JWST and others plan observation campaigns that could, in years, accumulate enough evidence for real clarity about DMs. In parallel, the ELT Extremely Large Telescope, under construction in Chile's Atacama Desert, with a 39-meter diameter mirror, will represent another leap forward in the ability to characterize exoplanet atmospheres. When it comes online in the second half of this decade, it will be able to study planets like K218b with unprecedented spectral resolution. The European Space Agency's Ariel mission, scheduled for the early 2030s, was specifically designed to study the atmospheres of hundreds of exoplanets in a systematic way. It will place K218b in a statistical context that does not exist today, allowing its chemistry to be compared with that of many other similar planets. And there is still the remote but real possibility that Webb's own accumulated data, in the next observations, will place the DM signal on K218b above or below the 5 sigma threshold definitively. That moment, if and when it arrives, will be unlike any announcement we've ever seen, because this time, the path to it will have been trodden with all the rigidity that a historical statement requires. Fermi's silence and Webb's hope. Let's go back for a moment to Fermi's question, where is everyone? The question assumes that if intelligent life is common in the universe, we should have heard something, some radio signal, some evidence of cosmic megastructures, some interstellar colonization that our galaxy should show if civilizations had had billions of years to spread. Silence has many possible explanations. Perhaps intelligent life is much rarer than simple life. Perhaps technological civilizations will destroy themselves before they can expand. Maybe interstellar communication just isn't as we imagine it to be, or maybe we're listening on the wrong frequency. But the February 2026 observation with the VLA and Meerkat of K2, 18 showed something interesting. Even without finding signs of technology, the researchers put important limits on it. If there's a civilization on K218b, it's not transmitting on radio with the power of our best radio telescopes. But that doesn't mean it doesn't exist. It's just that it's not screaming at frequencies that we can hear. And perhaps that is exactly the point. Maybe the first life we find isn't smart. It will not be a civilization. It will be a microbe, a colony of phytoplankton floating in an alien ocean, unknowingly producing the gases that will one day reveal their existence to a curious primate species 124 light-years away. If that happens, and when it does, whether it's on K218b or elsewhere, the world will never be the same. The closing, the question that will continue. There's one thing Avi Loeb said. In the midst of all the controversy over the K218b that has kept resonating, he talked about patience. About the time it would take for any signal we sent to that planet to be answered 248 years. About how it would be better to listen than to speak. And then he added, with the characteristic lightness of someone who has spent decades thinking about the cosmos, the best advice I can give is, first listen, then speak. There is a quiet wisdom in this phrase that goes beyond astronomy. Humanity has spent millennia talking about life beyond Earth. speculating, imagining, fantasizing, fearing, building stories of invaders and saviors, of parallel worlds and ancient civilizations. Our culture is saturated with extraterrestrial life that we invented. What James Webb represents is the first time in history that we are, in fact, listening, not with the vague hope that something will appear, but with specific instruments, calibrated for specific frequencies, analyzing data with rigorous statistical methods, listening with the precision that the question demands. And what we hear, for now, is ambiguous, a sign that could be life, or it could be chemical, a molecule that exists where life exists, but perhaps also where it does not, a planet that meets the right conditions, but about which we still have a lot to learn. Is it frustrating? Yes. Is it exciting? Absolutely. Is it the place where the most important science in the world is happening right now? Without a doubt, because K to 18 billion is not just a planet, it's a question. It's the oldest question humanity has asked, rephrased with the best tools we've ever had. And the answer, when it arrives, however it arrives, will not only be scientific, it will be philosophical, it will be historic, it will be transformative in a way that we have not yet been able to fully anticipate. For now, what we have is the signal, tenuous, ambiguous, contested, intriguing, and Webb keeps looking, and we keep listening. The next version of this story, when it arrives, will be stranger and more beautiful than anything we can imagine so far.